back. In the second video, we'll be analyzing an air cargo fleet assignment model. And let's start with the problem setting. We have a given set of aircraft types, and we'll be focusing on full freighters, a set of airports, and a set of cargo requests, each with a release time and a due date. And our goal is to find the most efficient way to route the aircraft fleet in the network while transporting requests. For example, we could have a ULD ready to be picked up in Amsterdam on a Monday morning at 8 a.m. And this ULD needs to be delivered in Singapore or in Lima or in Nairobi on a Tuesday evening. And we could have the same release time and due date for many other requests. And we want to use our set of aircraft in the most efficient way. So we want to transport as many requests as we can, as long as that's profitable. Of course, like many other models, we'll deal with some assumptions. First, the initial and final number of aircraft per aircraft type in each airport is given. Then, requests are already consolidated ULDs, but we do not consider potential feasible layouts for capacity, as we saw in the previous lecture. We just consider each aircraft as a single bin with a certain weight capacity, and we consider that a certain number of ULDs can be allocated to that aircraft as long as their cumulative summation in terms of weight is less than the weight capacity of the aircraft we are considering. And plus, we are completely neglecting the bin packing problem that assigns shipments to ULDs. We already consider a pre-filled ULDs. And finally, aircraft and ULDs as a consequence move in a network at discrete times. So we'll be relying on the concept of a time-space network. And actually, let me start with a recap on what a time-space network is. A time-space network is a network representation of a set of airports at different time steps. So we have two components. We have a spatial component given by the airports and a temporal component given by the time steps. And let's assume we have a set of NA airports, a planning horizon T, and a time step delta T, such that we can define a time discretization as follows. We have delta T, 2 delta T, 3 delta T, all the way up till we reach the big T, which is the end of our planning horizon. As such, we can define in our time-space network a set of nodes, which cardinality is NA, so the number of airports, times big T divided by delta T plus 1. And this is number of time steps within our discretization. If you think about it, we map every airport with the same number of time steps, and we replicate this for every airport we have. So pretty much, as such, each node in our network is a unique tuple defined by two indices, two numbers, an airport and a timestamp. For example, two nodes could be like this. We can have a node that says, okay, I'm in Amsterdam, so this is my spatial component, the airport, at 13 hours. And a different node could be here, I'm in JFK, New York, at 15 hours. In the following, I will drop in this case, the IATA code of the airport. I will just use an index for each airport, and I will do something similar for times. Instead of saying 13 or 15, I will start from 0, which is, let's say, the start of my planning horizon, and I will increase the time component by delta T or by whatever time interval is needed. So in principle, a time-space network in terms of nodes looks like this. In this case, we have 3 airports and we have 7 timestamps ranging from T1 to T7, which is our big T. And as such, this time-space network entails 21 nodes. But now we need to connect the nodes, right? So far, we just put nodes in a 2D Cartesian coordinate space, but we have no connections whatsoever between nodes. How do we connect nodes? First, we have ground arcs. Ground arcs connect two consecutive nodes in the same airport. So if we have two nodes, A1, T1, A2, T2, we have a ground arc if and only if A1 is equal to A2, so we are dealing with the same airport, and T2 is equal to T1 plus delta T, which means that we are connecting consecutive nodes in the same airport. And let me consider, for example, our first airport in our network, and let's consider a planning horizon of 96 hours and a time step of 4 hours. As such, our ground arcs for this airport will look as follows. Of course, I'm not considering the central part because otherwise I would have needed a much wider slide. But we connect node 1, 0, which is the first node in that airport, airport 1 at time 0, to node 1, 4, all the way to the right to 192 and 196. So again, using our example with the 3 airports, 7 timestamps, this is the full set of ground arcs. But now we also want to define flight arcs. And flight arcs, they connect different airports, and in terms of time, that really depends on the flying time between the 2 airports. Actually, the formula we use is there's a connection between 2 airports such that T2, so the timestamp in the destination airport, is T1 plus this expression you see right there, which basically defines a multiple of our delta T, and the multiple is such that we consider the flying time. Then I'm mentioning LTO, which stands for the landing and takeoff extra time an aircraft might need before takeoff and after landing, and TAT stands for minimum turnaround time. And the reason why we use turnaround time already in the definition, let's say, of the augmented flying time between 2 airports will become a bit easier to understand later in the presentation. It has to do with the flow conservation constraints. And in addition, I'm using the ceiling operator. So one thing I didn't mention yet about the time-space network is that the notion of time is only associated with multiples of our delta T, which means that we cannot have continuous time. So if we have an overall flying time which is 2.5 times our time discretization, for us that will be rounded up to 3 times our time discretization. And let me hopefully be more clear with this example. Let's consider flights from airport 1 to airport 2 such that the actual flying time is 5 hours. We have an LTO time of 0.5 hours and a minimum turnaround time of 1 hour. If we use the formula and keep in mind our time step is 4 hours, our numerator would be 6.5 hours. But actually 6.5 is not a multiple of 4, which means that for us, this flight, which overall would take 6.5 hours, is overestimated to 8 hours. But this is a natural consequence of a time-space network, and we have to deal with that. Of course, the larger our time step, the coarser, to some extent, the approximation. And again, just to provide you an example, in our case, this could be 2 flight arcs between airport 1 and airport 2. So we connect the 2 airports, so the first 2 elements in each node are 1 and 2, so the 2 airports, and we go from time 0 to time 8, or if we move 1 step to the right, from time 4 to time 12. And as you see, the difference in times is 8. So again, it's an overestimation of the original number, which was 6.5. So again, here I'm not plotting all the potential flight arcs. Of course, they depend on many factors, on, for example, the range considerations. Not all airports are connected because maybe there's not a direct connection between airports, right? So this is just for graphical purposes. And if we retrieve our ground arcs, this is, let's say, the full time-space network for this example in terms of nodes, in terms of ground arcs, and in terms of flight arcs. So basically, what can we say more about ground arcs and flight arcs? Usually for ground arcs, the number of aircraft of a specific type using an arc can be an integer, so which means that it can be greater than 1. And that basically means that you can have 3, 4, 5 aircraft of the same type staying on the ground. Because if you think about it, that's the definition of a ground arc. If an aircraft or if a set of aircraft rely on a ground arc, it means within that time step they do nothing. They are just staying on the ground in that airport. On the other hand, for flight arcs, this really depends on the time discretization and some other assumptions. But in this model, we assume that at most one aircraft, considering all fleet types, can use a specific flight arc. So a specific flight arc either is not flown at all, or a specific aircraft of a specific fleet type will be using that flight arc. So this is an example which already entails a bit of flow conservation. We have 3 aircraft of a specific type, which here is not specified, using the first ground arc. And then what happens is 2 of them will stay on the ground, will remain grounded, and 1 of the 3 will actually use a flight arc to move to a different airport. All right, so far we only focus on aircraft. So far I didn't mention cargo requests at all. So what can we do with cargo requests? As I mentioned before, they can become available at a specific time in a specific airport, and they need to be delivered at a different airport, most likely within a certain due time. But the release time and the due date or due time, they can be whatever number they are. One release time could be, okay, this ULD is available Monday morning at 6:45 a.m., but maybe 6:45 a.m. is not consistent with our time discretization. As such, we need to define a source node and a sink node for each request. And for each request, the source node is the first available node in the origin airport with a time greater than the release time of the cargo request, while a sink node is the last available node in the destination airport with a time which is smaller than the due date. So let's consider this case. This is the same cargo request. In A1, that's the origin, so where the ULD appears in the system, and in A2, that's where the ULD should leave the system. And if you see, the release time is somewhere in between T1 and T2, and the due date or due time is somewhere in between T5 and T6. So what we do is as follows. For us, the actual release time becomes T2, so then the source node of that cargo request is basically A1 T2, while the destination node will be A2 T5. So we basically push the request a bit forward in time for the source, and we push the request a bit backwards in time for the sink, for the destination. Additionally, a cargo request can move freely in a time-space network as far as we consider ground arcs, because if there's a ground arc, it doesn't really matter if a cargo request is associated to an aircraft or loaded onto an aircraft or not. On the other hand, a cargo request can only use a flight arc if we assign an aircraft to that flight arc. So let's assume we have these 3 possible paths for this request. But let's assume we assign 2 aircraft to the green and the black flight arc, but no aircraft to the red one. That means that request won't be able to follow the red path because there's not an aircraft capable of carrying that request from A1 to A2. In addition, we allow some requests not to be transported. And the way we do that is, again, it will become more clear when we define the model more specifically. We can define what's called a no-service arc. A no-service arc is basically a mathematical trick that directly connects the sink and the source node of our request without moving explicitly through our original time-space network. And if we use this arc, basically we are mathematically delivering the request to destination, but in practice we are deciding not to transport the request in the first place. And as such, this arc should be, for each request, should be associated with a penalty which is high enough to make the model avoid this arc unless it's the only feasible solution somehow. And after this introduction with the time-space network in general and a bit more tailored for our model, let's actually dive into the fleet assignment model. As usual with every MILP model, let's start with some sets. We have a set of nodes indexed by n, a set of fleet types, big N, set of nodes indexed by n, big K, which is a set of fleet types, which is indexed by k, R, set of requests indexed by small r. We have three sets of arcs, AF, which is the set of flight arcs, AG, which is the set of ground arcs, and AS, which is the set of no service arcs. And overall, the overall set of arcs is the union of AF, AG, and AS. They are also mutually exclusive, so when we are carrying out the union, there's no repetitions. And just one note, before I told you each node was a tuple with an airport and a timestamp, right? A timestamp, sorry. Here, for sake of simplicity, we index nodes with only one index, n. But please do not forget that for each n, in practice, we have the tuple. So we have a spatial component, a specific airport, and a temporal component, a specific timestamp. But again, for sake of simplicity, I will be just using n. But again, n for us means a specific airport and a specific timestamp within our time-space network. We also have a set of parameters, namely df, the length of a flight arc f, wr, the weight of request r, PCR, which is a monetary penalty per unit weight if a certain request is not transported, WK, which is the weight capacity of aircraft of type K. Then we have CFK, which is the operational cost per unit distance of aircraft of type K when traversing a flight arc. And we have MCF, which is the marginal cost for transporting a request per unit distance and unit weight along flight arc F. Why do we have a marginal cost when we transport a request? Because there are some costs associated with the act of transporting a request. For example, we might have a bit extra fuel to carry, which we need to pay for. We need to pay people to actually load the request. So there's many things which could go towards this marginal cost. In addition, we define a few parameters. We define parameter H and K, and this maps how many aircraft of type K enter, and we'll use a minus, I'll show you later why, or exit with a plus, the network in node N. And given that for us aircraft can enter the network only at the first time, so we know the initial location pretty much, and they can only exit the network at the final time, this H can only be negative for nodes where the time is the first timestamp of our discretization, and can only be positive for nodes, let's say on the right side, so nodes where the timestamp is the end of our planning horizon. For all intermediate nodes, this H will be 0. So let's consider this case, again, our example with the 21 nodes, and here I'm already using a single index for nodes. We have two aircraft of type 1 entering the system in node 1. One of them should exit the system in node 7 and the other one in node 14. While we have a single aircraft of type 2, it enters the system in node 8 and it exits the system in node 21. In this case, these would be the numbers. So we have a -2, H11 is -2, H82 is -1, H71 is 1, H14 is 1, and H21 2 is also 1. And just an extra note, the summation of all H's for a given K across all nodes should be 0. And this means that whichever number of aircraft of a specific fleet type we initially inject into the system should also leave the system. So this is a first check. If the summations do not coincide, it means somehow an aircraft either appears or disappears all of a sudden within the network, which is not possible in our case. We can do something similar for requests. We define basically the same parameter VNR, and again it maps if a certain request R enters minus or exits plus the system in node N. Here, since we are using this for each request, the only number different than 0 is 1, because we do this for each request. Additionally, as we saw before, requests can enter or exit the system not necessarily at the first time and at the last time. They could enter and exit the system pretty much at any time. It really depends on the release time and the due date, which means that potentially we can have non-zero entries throughout the nodes. Let's consider this case. We have request 15 that enters the node, that enters the system in node 9, and it must exit the system in node 20. So we would define v915 to be -1 and v2015 to be +1. All right, let's carry on with decision variables. The first one is xfk, which is a binary, and it is unitary if flight arc f is used by aircraft type k and 0 otherwise. Then we have ygk, which is an integer. That's the number of aircraft of type k using ground arc g. And finally, we have a second binary, a decision variable zar, which is unitary if arc A is used by request R and 0 otherwise. And now let's dive into the formulation in terms of objective and constraints. All right, the objective. It's a minimization problem, and we have 3 terms. The first term maps operational costs due to flying an aircraft along a specific flight arc. And as such, here we are not considering the payload yet. The second term maps the additional cost associated to carrying requests on board. And something I didn't mention before, our marginal cost only depends on the flight arc and not on the aircraft type, which might and could be reasonable actually. The reason for that is if you want to do that, the formulation becomes a bit more challenging, but I'm happy to discuss that with you if you're interested. The third term is a penalty for every request that is not transported. And with YSR, we define the specific no service arc for request R. So there's one YSR for each request, and that's unitary if the associated no service arc is used. And as I told you, this is a minimization problem. We are basically minimizing costs. But we could consider revenue as fixed, so we can assume that all the revenue from the requests was already obtained. Although in practice, usually customers, they do not always pay before and so upfront. So this could be quite an assumption. But in principle, if we consider revenue as fixed, our profit maximization problem becomes some minimization of costs, because we can remove the revenue from the maximization since it's fixed. And maximizing minus the cost means basically minimizing our costs, right? And then let's finish off with our constraints. The first one is as follows. It basically implies that every flight leg can be flown by at most one aircraft. And by one aircraft, I mean one aircraft of a specific type. And please be careful, it's a smaller or equal type of constraint. It's not an equal, which means that many flight legs most likely will not be flown in our time-space network. This looks a bit nastier, but it actually is not. This is flow conservation constraint per each node and per each aircraft type. We are basically saying that whatever enters a node, given a specific aircraft type, should also exit the node. And we use 2 sets, delta plus n and delta minus n. Delta plus n defines the set of arcs arriving at node n, while delta minus n defines the set of arcs departing from node n. And for example, if you have node 5 and this set of arcs, delta plus would be 25, 32, and 55, the 3 arcs entering node 5, and the 4 exiting arcs composing delta minus 5 will be 18, 78, 103, and 155. And note that we have 2 terms with a minus, so we have the contribution from the flight arcs and the contribution from the ground arcs, and same we have 2 terms with a plus, contribution from flight arcs and contribution from ground arcs. And the reason why I was using a negative number for the source of an aircraft, or of in this case it's still an aircraft, is because I'm using the minus for delta minus, which is a set of arcs leaving a node. And if you consider a source node for an aircraft, let me see if I have my pointer. This is the term which will be probably 1 or greater than 1, because this is the set of arcs leaving a node. And if this is a source node for a specific aircraft type, we'll expect this number to be positive, but since we have a minus here, we also want this number to be minus. And same when a specific aircraft of an aircraft type arrives in its destination node, in its sink node, this will be a positive number, which entails that this will also be positive. We have the same type of constraint, so flow conservation, but now it's for requests. And now it's simpler because while for aircraft we differentiate between ground arcs and flight arcs, for each request, it doesn't really matter if a certain request transverses a ground or a flight arc, as long as we satisfy flow conservation. So again, here it's the same as before. This is the set of arcs leaving a certain node. Sorry, entering a certain node. No, sorry, leaving a certain node. And this is a set of arcs entering a node. And we want conservation of flow here as well for each request in each node of our system. And finally, we have weight capacity per flight leg, which should be satisfied. The left side of this constraint basically entails that if we are carrying some requests along a flight arc, we are summing all their weight contributions. And the right side basically defines the capacity along that flight arc. And it's easy to see that if a flight arc is not served by any aircraft type, all the XFK for that flight arc will be 0, which means that we cannot carry any request at all along that flight arc. While if the right-hand side is, if this decision variable is unitary for a specific aircraft type, and it can only be unitary at most for one aircraft type, as we discussed, this WK will be activated, so we'll have WK tons available to use. So this defines an upper bound which is either 0 if we don't fly at all that flight arc, or WK if that flight arc is flown by an aircraft of type K. And let's finish off with the nature of the decision variables. As mentioned before, XFK is binary, GK is integer because we can have more than one aircraft of a specific type grounded, so moving between the same airport forward in time. And ZAR is also binary because we are focusing on each request. So it's if a request moves along a specific arc or not. And let's just quickly recap some potential limitations of the model. For example, the beam packing part is quite a strong approximation. We consider pre-filled ULDs and assume they will fit in the aircraft as long as their overall weight is below the weight capacity, which might not always be the case. For example, how about the ULD positions on deck, which we saw in the previous video? How about volume? You might not know that many flights, when it comes to cargo, are volume bounded and not weight bounded. So weight-wise, we might be still in a feasible situation, but volume-wise, we might be trying to carry more volume than the actual volume available in the aircraft. And more importantly, how about shipments? We are translating two 3D beam packing models, so shipments to ULDs and ULDs to the aircraft deck, into a single 1D beam packing model. How about weight and balance constraints, which we also covered last time? Remember, this is actually what happens in practice. We are putting shipments, which are 3D in nature, inside an ULD, and then we need to position ULDs properly on the aircraft deck. And what is another, this is a bit trickier, but what is another potential limitation of the model, more on the algorithmic side? The size of the problem can explode when many requests are considered. Basically, the same could be formally set for the fleet, but usually the fleet is much smaller than the number of requests that potentially can enter and exit the system. So in general, what we want to do is we want to replace an arc-based decision variable ZAR with something more efficient computationally. And in this kind of problems, a possible solution is column generation, which will be treated in the next video. In principle, the main insight is when we define a time-space network, many arcs will not be used. So because we are only using a very small subset of all the arcs we define. So is there a way to avoid somehow to define all the arcs in the first place? And that's where column generation comes into play. But that's the topic of our next video.